Hi everybody. This is joint work with Christos Jamos, who's on a trajectory to Wisconsin-Madison, and Manolis Zambetakis. And it's about the expectation maximization algorithm, which I'm about to explain. So the goal of the algorithm is to solve a maximum likelihood estimation problem for models with latent variables. So the situation we're talking about is, imagine you have a parameterized family of distributions, parameterized by lambda, and you imagine drawing a lot of samples from that distribution, except you can only partially observe them. And the goal is, given only partial samples, to estimate the underlying parameters lambda. So if you write the MLE for this problem, so this is the log likelihood. It contains, so I'm summing over all my samples, the log of the probability of the sample. So now this probability is a sum over the state of the latent variable in that sample. So this log of sum usually turns the problem non-convex. So it's challenging to do maximum likelihood. And the EM algorithm is a beautiful method that addresses this problem. Okay? I don't have time to explain the method. Ask me at the poster session, but let me actually show a picture that captures what's happening. So in such a problem, the log likelihood function is some non-convex function like this, and the EM algorithm is called EM because it has two steps, the E step and the M step. So what the E step does is, imagine at some point during the trajectory of the algorithm, the current estimate of the underlying parameters is this lambda t, okay, which is somewhere in the likelihood landscape. So what the E step is going to do, it's going to construct, the EM algorithm provides a very canonical way for constructing a concave lower bound to the likelihood function that actually touches the function at the current iterate. So in particular, what the M step of the algorithm does is it optimizes this concave function, which is an easy computational problem. And because this concave lower bound touches the likelihood landscape at this point, you're making progress towards optimizing your likelihood. And of course, you may get stuck in local optima. But it's a beautiful algorithm that always makes some progress if there is progress to be made. So it applies in very general setting. It was proposed in the 70s. It has a ridiculous number of actual citations. I was really surprised by it. It is very high in this pile of all papers ever written. Nevertheless, there's actually absolutely no case where it's known to converge to the maximum likelihood estimate. Okay? On the contrary, it is known that it fails if you don't initialize it properly. So our contributions is to provide the first known global convergence guarantees for this algorithm for mixtures of Gaussians, as we're going to see. And we also provide some general purpose methodology for establishing global convergence guarantees for non-convex optimization methods. So the model in which we're going to be applying the algorithm is a very simple one, okay? It's a mixture of two Gaussians. The weights are known to be half and half. The covariance matrices are also known and they're shared. So both of the components have the same Gaussian matrix, the covariance matrix. So the only thing that's unknown are the centers of the two Gaussians. So in this scenario, the EM update looks like this. It looks like a complex formula, but really what you're doing is basically, these are the samples that you observed from the mixture, and you're really averaging your samples, the samples that you got. The weights that you're using are your beliefs that these samples came from the first component. Okay, so given the current parameters, my belief that this sample came from the first component is the Gaussian centered at lambda, my current guess, over the mixture density, right? And this is just renormalizing. So this is really what it's doing. It's really a soft two-means algorithm. So in this picture, I'm showing the the 2 mins, which is the hard version of the. So, in this simulation, like, my points are hardly assigned to one of the 2 cluster centers. What EM does, it does a soft assignment according to the current beliefs that each sample came from the 2 cluster centers. And you update the cluster centers. Right? So this does a combined step. So you assign each point at the corresponding center with this weight, and then you're recombining you do a weighted averaging of your samples to find the new cluster center, and you keep going. And I have parameterized my mixture so that one cluster center is at mu, the other is at minus mu. So there's only one thing that I'm iterating over. Okay, so what is our main result? Our main result is that the EM algorithm for this model converges to the truth from essentially every initialization. And we characterize the speed of convergence, and in fact, the speed of convergence is geometric. So at every step, you improve by a constant factor your distance to the truth. Summarized by this picture. So this picture is the generic picture of what happens in this model. So at every step, you're improving your distance to the truth. This is Mahalanobis distance by some factor that depends on where you are. And in fact, this factor becomes better as you keep moving, so you're accelerating your speed towards the truth. Now, the factor depends on your angle with the truth. So here you have bad speed of convergence. Right? So this is an example where the truth center is mu. So obviously, the picture is symmetric, so this is also as good a solution as this one. So there are 2 stable fixed points and only 1 unstable fixed point at the 0. Okay? And our theorem says that as long as you do not start equidistant from the 2 possible solutions, you're actually geometrically converging to the truth. Right? And the speed, again, depends on the angle you have with the truth or the norm that you have. Okay? So, just to give a sense of the title, at least, of the paper. So in 1 dimension, and if your signal-to-noise ratio is 1, which is a bad case, really it's like not a bimodal thing, it's a unimodal thing. If you start arbitrarily far away from the truth, in 10 steps you're 1% error from the truth. Hence the title of the paper, 10 steps suffice. So now, the finite sample complexity says that if I want to achieve a Mahalanobis accuracy epsilon, I need to pay linearly in the dimension over epsilon squared, which is optimal up to the log factors hidden here. Or if you want to look at the error rate of the algorithm, it's, again, essentially optimal. So just to compare to independent and prior work, so independent work of Xu, Su, and Malecki from NIPS also proves global convergence guarantees for the exact same model. But they only look at the population version, where they have infinitely many samples from the mixture. And they do not provide explicit rates. Prior work of Balakrishnan et al. Provides only local convergence guarantees, and also assuming separability. So I don't have too much time to talk about proofs. Let me just show you a generalizable vignette of the proof. So here's an abstraction of the EM iteration, right? So the EM iteration depends on my current iterate and also the truth. The truth is providing me samples. My current guess will affect where I'm going to go next. And just to give you a mental picture of how it looks, it has some tanches and so on and so forth. So it doesn't matter what it is. The classical approach to show that an iterative method converges is to establish contraction. So if you show that this function, for every instance, okay, it's contracting with respect to the current iterate, then by Banach's fixed point theorem, you get a unique solution and you have global convergence to that solution. The problem is that the EM algorithm is actually not contracting. Right? So it's not a contractive map, the iteration that EM does. It's only contracting close to around the truth. Hence, that's why we have a lot of local convergence guarantees for the EM algorithm, but we don't have any global convergence guarantees, just because it's really not contracting globally. It's contracting close to the truth. So we flipped the problem on its head. So instead of showing contraction, we actually do the following interesting idea, which is generalizable. Instead of showing contraction of the iteration with respect to the current iterate, we actually look at its sensitivity with respect to the instance, with respect to the truth. So what we show is that if the update is sensitive with respect to the truth, then that implies making progress towards a solution. And the picture is this, that if your update is sensitive with respect to the truth, this is the truth, this is your current iterate, this is where you're going to go next. If you're sensitive with respect to the truth, this means that if I move the truth from here to there, if your sensitivity implies that, it's, the change of the instance is, carrying you with the instance, right? So intuitively, that implies that you're making progress towards the truth, if you're sensitive with respect to the truth. So that's basically it. So this is a summary of our contributions. And if you want more information, please see our poster. Thank you.
Any questions? Yeah.
So maybe I missed something, but it seems that your contraction rate is depending on your sequence of iterates?
The contraction depends on...
Can you please repeat the question?
Sorry, yeah. So the question is, does our contraction rate depends on the sequence? It does not depend on the sequence, it depends on where you currently are. So it depends on your norm, your current norm, and your current angle with the truth. But we can guarantee that, if you want to look at this contraction as a function of time, it is accelerating towards the truth. So in particular, the initial contraction is what, the initial contraction is the worst possible. So in particular, you don't want to start in this area. And, I noted it here, but I didn't talk about it. We provide a bootstrapping method using EM itself to actually initialize it in the blue region, so where contraction is fast. Yeah.
For this parameter, for the mixture of Gaussian, how general do you think is global convergence?
So for mixture of Gaussians, we know that it's not, the reason why there haven't been so many results for EM is that basically it is not going to be globally convergent, okay? So our motivation here was to show one case where it is and develop general machinery like the sensitivity argument for other methods. We know, for example, that if I make the weights instead of half-half, 1/3, 2/3, we have examples where there is a big basin that gets you to a spurious fixed point.
Let's take the questions after the talk. After the session.
Thanks, guys.